Okay, continuing on with this section, this example number 2, we've got 2/3, and then we need to do 1 times f of 4. Well, we have f of x is equal to x squared, so 4 squared is 16, plus 2 times 16 squared over 9, plus 2 times, not f, 2 times 20 squared over 9. So we're just squaring all of our x values, plus 64. Okay, so all of that we have, let me see, how did I write my answer? Yeah, I just have my decimal. So go ahead and figure out what your answer is from there. I have it as a decimal. So 150.5185. Okay, and then our exact value, we want to know what our exact value is. That's the 100. So our first solution would be 149.3333. And then the error in the approximation is going to be the difference of those two numbers. So our error is going to be 149.3333 minus 150.5185, absolute value of those. And then that answer is, I'll put it up here, this is where our solution goes, so 1.18517. That is our error. This is our exact value. Yep, and that's all we need for example number 2. All right, the last thing, almost the last thing. We have one little tiny more thing we're going to go over. But the next thing is error bounds from midpoint trapezoidal rules. Those go together in this box up here. Okay, here is our equation, and here is our equation. And then also the error bound for Simpson's rule. Now, we're not always able to figure out what the exact value is. That's our whole purpose for being able to use numerical integration, is that we can't find the exact value. So they've determined a way to find what our error is, and we're not going to go over the proof of this. This is not proven here. But this is our equations that we are given. So let f of x be our function between a and b, so that's our limits of integration, and our second derivative, f double prime of x over the interval. If m is the maximum value of the absolute value of the second derivative of x between a and b, then our upper bounds for m sub n, so remember this means our approximation using the midpoint rule with n subintervals, and our approximation using the trapezoidal rule with n number of subdivisions. When we use that to estimate an integral, the error is n, which is the greatest value of your second interval, times b minus a, which b and a come from your limits of integration, cubed over 24 times n squared, where n, remember, is the number of subdivisions. So that's what we're going to do to find our error for our midpoint rule. So write that equation down. Make sure you have that somewhere so it's easy to look for when you're doing your homework, and again for the review, and then also for the test or for the final. And then here we have trapezoidal rule using n number of subdivisions. And then we have m, which again is our second derivative, the maximum value for our second derivative of, I should say. Then b minus a cubed over 12 this time, n squared. So see the difference between those two? One is 12, one is 24. Now if we skip down here to our error bound for Simpson's rule, this one we have is totally separate because our capital M is now the largest value of the fourth derivative. Okay? And then also we have now m, which is our greatest value of our fourth derivative, of b minus a to the fifth over 180 n to the fourth. So Simpson's rule error bound is quite different than the other two. So make sure you have those equations written down so that you can use those. And we'll move on to our next example. So example number 3. In estimating the integral from -1 to 2 of cosine of 5x dx using the trapezoidal and Simpson's rule with n equals 4, we can estimate the error involved in the approximation using the error-bound formulas. So we're not asking you to find the integral or to find any estimation. All we're asking for is the error, which we can do with those equations that were just given. So our error for trapezoidal rule first. So the error bound for the trapezoidal rule, so t sub n is going to be less than or equal to m, which is the greatest value of the second derivative, and then b minus a, which is our limits of integration, cubed over 12 times n squared, where n is your number of subdivisions. Okay? Just as close. Okay. And then s sub n is less than or equal to m, which for Simpson's rule, m is going to be the largest value of the fourth derivative of f of x. So m times b minus a, and this time it's going to be to the fifth over 180 n to the fourth. Okay, so let's go ahead and start with t sub n. We need to find what the error will be, less than. So t sub n is less than or equal to m, so we need to find the second derivative. For this one, we're also going to need to know the fourth derivative for Simpson's rule. So start off with our function. Our function is equal to cosine of 5x. So our first derivative, so derivative of cosine is negative sine. So negative sine of 5x. Cannon, where are you going? And then we have to remember our chain rule. So multiply by the derivative of the inside. Okay, second derivative is then going to be negative cosine. I need to leave myself a blank. We'll come back and put that in there. So negative cosine of 5x times 5, and then we also have the 5 out there in front still, so negative 25 cosine of 5x is our second derivative. Then our third derivative of x is going to be equal to, we're going to have to bring this 5 out again for our chain rule, so and integral of cosine is negative sine, so now we're back to positive. So 125 sine of 5x. Okay, and then just one more. So f to the fourth of x. So the fourth derivative of x is equal to, multiply out front by 5 again. So 625 this time, right? So 625 cosine of 5x. Okay, so for trapezoidal rule, we need to know what the maximum value of the second derivative of our function is. So let's go to Desmos and look at that. Okay, so let's go to Desmos and look at, this is the second derivative, so negative 25, you can't see that here, let me see if I can pull that, I don't know if this works or not, but see if that'll pull your screen over. Okay, so negative 25 cosine of 5x, and then this is what our equation looks like. So it's a cosine function, we should know all of this, it's got an amplitude of 25, its midline is going to be right at 0, so the highest that it possibly could get is 25, and so we just have to make sure that it actually hits its peak. somewhere within our interval, which is from -1 to 2. And it hits the peak multiple times between there. So we know the greatest value that this function can take on between our interval of -1 to 2, greatest value is 25. Okay, so that's all we need to know. That makes m 25 for our equation. So t sub n is less than 25, and then b to a is going to be our 2 minus -1, so those are limits of integration, and then cubed over 12. N is 4 in this case. Right here it tells us that, so that's the number of subintervals. So calculate all of that out, and you will get 3.515625 for the error if we use 4 subdivisions and the trapezoidal rule. Okay, so without even finding any kind of integration, anything like that, the only thing that we do have to do is the derivatives. We can figure out what our error will be. At least, it could be less than that error. That's our maximum error. So let's figure out what Simpson's rule now. So S of n is less than or equal to n. Now this time for n, we need to look at our fourth derivative. So now it's at 625 cosine of 5x. So when you're looking at that one, same thing, we know what the amplitude is on that cosine function. Highest value that it could take on is 625. So you need to look at your intervals between -1 to 2 and see. Now we've already looked, we have not changed the period of that function at all. So we already know that within that interval, this cosine function takes on its highest value more than one time. So we know for a fact it's going to hit its highest value, which in this case is 625. And so that's going to make m 625. Okay, then do b minus a, so 2 minus -1. In this case now, for Simpson's rule, we're going to go to the 5th power over 180 times n. Sorry, let's go ahead and put that in. So 4 to the 4th power. Calculating all of that, we get 3.29588. So when we ask for an error bound, that is what we are talking about. Use those equations, figure out what the error bound is for both trapezoidal rule and the Simpson's rule for this one. On this one, you can see that the Simpson's rule is going to be the closer approximation. Also, the other thing that we can change is we can change the number of subdivisions we have. That's an easy thing to change when we're doing this numerical integration. Just make that n value a little bit bigger. It does take more work when we're doing our trapezoidal rule and our Simpson's rule because we have more endpoints. So we don't want to make it too huge, but by using this error bound method, we can figure out what our error will be and how close we want to be, and the n value is the number that we could play around with. So if we wanted to be closer than 3, then we would just make n bigger. If 3 was close enough for us, then we just go ahead and use 4 subdivisions for this one. Okay, so let's go on to our next example.